In the last video, we talked about absolute maximum and absolute minimum values of a function on an interval. Now we're going to look at a technique called the closed interval method and how we can find these absolute maximum and minimum values. So the closed interval technique, to find the absolute maximum and minimum values of a continuous function f on a closed interval AB, first we're going to find the values of f at the critical numbers of f. And recall, finding the critical values of a function we're going to look for where the derivative equals 0 or where the derivative is undefined or does not exist. That's how we're going to find our critical numbers for part 1. Part 2 says find the values of f at the endpoints, and typically those are given to us in a problem. They'll give us a range of values that we're looking for, the absolute maximum or absolute minimum. And then what we're going to do is we're going to plug the critical numbers into the function and compare those values with the endpoints. So we'd plug the values of the endpoints, or the x values of the endpoints, into the function and compare it with the critical numbers. So if we had a critical number f of c sub 1, and let's say we had two critical numbers, we would take those, plug them into the function, and also we would plug in the endpoints a and b. And then we would look at the values of each one of these. The biggest number would be the absolute maximum value, smallest number, absolute minimum value. So that's the closed interval method. Find the absolute maximum and minimum values of the function x cubed minus 3x squared plus 1 on the interval -1/2 to 4. First, we're going to find our derivative so we can find our critical numbers. So f prime of x equals 3x squared minus 6x. Now we will set this equal to 0, and we can factor out a 3x, and we'll set each one of these factors equal to 0, and we get x equals 0, x equals 2. So there's step 1, finding our critical numbers. We have critical numbers at x equals 0 and x equals 2. Second, we're going to identify our endpoints. Our endpoints are at x equals -1/2 and x equals 4. Now we're going to take our critical numbers and our endpoints and plug them into the function, because we want to find the absolute maximum and minimum value of this function. So we're going to plug in, and I'll try to put these in order. F of -1/2 is an endpoint, and we have f of 0 from one of the critical numbers, f of 2 from another critical number, and then f of 4 is our other endpoint. Now when we plug these into our function, if we plug -1/2 back into our function, we would get 1/8, and look at this one here. If we plug 0 into our function, we should get 1, and if we plug 2 into the function, we get -3, And if we plug 4 into our function, we get 17. So now we're going to compare these values. The largest value is 17. So that is our absolute maximum on this interval. And now we're going to look for the smallest value, which is -3. So this would be our absolute minimum value on this interval. So that's the closed interval method. We find our critical numbers by setting the derivative equal to 0, and we also look to see where the derivative is undefined or does not exist. In this particular case, we can see the derivative is never undefined, so we didn't get a critical number from that. Second, we looked at our endpoints. And then third, we plug those values, our critical numbers and our endpoints, into our function, and then just look for the biggest number, which gives us our absolute maximum, and the smallest number gives us our absolute minimum value. So here we found our critical numbers. There are our endpoints. And then we found our absolute maximum and our absolute minimum values. Estimate the absolute minimum and maximum values of the function f of x equals x minus 2 times the sine of x on the interval 0 to 2 pi, 6.28, 2 pi. So first, we need to find our derivative. So f prime of x equals 1 minus 2 cosine of x. We set our derivative equal to 0. We're trying to find our critical numbers. Solving for x. Now if we subtracted 1 and divided by a -2, we would get cosine of x equals 1/2. Now thinking about our unit circle, the cosine is positive in quadrants 1 and 4, and we know the cosine of pi over 3 equals 1/2, so that would be one solution, x equals pi over 3. And then our reference angle is pi by 3, so to find the angle in the fourth quadrant, we would take 2 pi minus pi by 3 and get our common denominators. 6 pi over 3 minus pi over 3 would give us 5 pi over 3. So there's our second critical number. Second, we need to identify our endpoints. We have x equals 0 and x equals, now I'm just going to write this is supposed to be 2 pi, so I'm going to write it as 2 pi. Okay, step 3. We're going to plug these values, our critical numbers and our endpoints, back into our function. So if we try to put these in order, f of 2 pi. So we would get f of 0, if we plugged 0 back into our function, you'd get 0 minus 2 times 0, 0. Now if we plugged in pi by 3, I'm going to go ahead and convert these into a decimal approximation so we can compare them easier. So these should be approximately equal to negative 0.685. And again, we're just plugging pi by 3 into our function, back into our function. And f of 5 pi by 3 would give us 6.968. And f of 2 pi would give us 6.28. Now we're going to look for the greatest value, and that occurs here. So that is going to be our, I'm going to have to abbreviate, don't have enough room, absolute maximum. And then we're going to look for the smallest value, which occurs here, which is our absolute minimum value. Let's take a look at the graph of x minus 2 times the sine of x and see if we can verify what we found. We found our absolute minimum at pi by 3 and our absolute maximum at 5 pi by 3. The Hubble Space Telescope was deployed on April 24, 1990 by the Space Shuttle Discovery. A model for the velocity of the shuttle during this mission from liftoff at t equals 0 until the solid rocket boosters were jettisoned at t equals 126 seconds is given by, here we have a velocity function, v of t. So that's the velocity of the space shuttle. Find the absolute maximum and minimum values of the acceleration of the shuttle between liftoff and jettisoning the boosters. Now, to find the acceleration function, we would take our velocity function and take the derivative of that function. That would give us our velocity function. So if we take the derivative of our velocity function, we get our acceleration. So this represents our acceleration function. Now thinking about this problem, we are trying to find the absolute maximum and minimum values of the acceleration. So we don't want to set this equation equal to 0. This is our acceleration function. When we're trying to find a maximum or minimum value of a function, we find its derivative and set that equal to 0. So to find the absolute maximum and minimum values for the acceleration function, we are going to have to take the derivative of the acceleration function and set that equal to 0. So we can apply the closed interval method on this problem. The derivative of our acceleration function is here. So if we set this equal to 0, this will give us a critical number. So we get t equals 23.12 seconds. So that's a critical number. Now let's identify our interval. We said our interval was from 0 to 126 seconds. So here we're plugging this critical number and our intervals back into the acceleration function now, because we're trying to find the absolute maximum and the absolute minimum value of our acceleration function. We compare these values and we see that at 126 seconds we have the largest number, 62.87. So that would be our absolute maximum acceleration. And then we look for the smallest number. And that occurs at 23.12 seconds, our critical number. And we get a value of 21.52. So we have found the absolute maximum value, and we have found the absolute minimum value.